All right, so we have another math problem. Let's go ahead and jump in. A patient ventilator system check reveals the following information. A PIP of 28, a PEEP of 6, a plateau pressure of 16, an I time of 0.8, and a respiratory rate of 18. Calculate the mean airway pressure. So let's go ahead and jump in. Okay, so first things first is we're going to have to do the total cycle time equation. And for this, we are looking at 60 divided by a respiratory rate of, where was that? 18. And our total cycle time is going to be 3.33. Now that we've done that, we can effectively plug everything into our equation. So we'll start just going straight down the line here. I like to change the fraction into a decimal every single time, percentages and fractions. Decimals is what you want them to be in these math equations. So let's see here, our peak, 28. Our PEEP is 6. Our TI, 0.8. We're dividing that by our total cycle time, just 3.33. Plus 6. We're putting that PEEP in there again. 0.5, 22 times, we'll do this math here, and that is 0.24 plus 6. Continue to work our problem left to right. Parentheses first, remembering that PEMDAS. 22 times 0.24, 528 plus 6. We would multiply first and then add, and we're going to get 8.64 centimeters of water pressure. So that's just an example of an equation that we might run into for mean airway pressure. All right, we have a cardiac index equation, and I'll read it. Calculate the cardiac index for a patient with the following data: heart rate of 70, stroke volume of 50, and body surface area of 2. Take note of our measurements. We'll jump right in. So we'll start first with getting cardiac output. Heart rate of 70, stroke volume of 50, and we're in milliliters. And that's going to give us 3,500 milliliters. And we will convert that into liters, just carrying over that decimal. So our cardiac output is 3.5 liters. And we'll take that over here to our cardiac index equation, 3.5, again we're in liters, divided by our body surface area of 2, and that's going to give us a cardiac index of 1.75 liters a minute. All right, guys, and that is cardiac index. All right, we have another equation here, and it looks like we need to figure out cardiac output using the FICK principle. I'll read the problem. A patient with an oxygen consumption of 400 milliliters per minute, arterial oxygen content of 18.5 volume percent, and a mixed venous oxygen content of 14.5 volume percent has a cardiac output of what? All right, so we'll just plug in our numbers. Oxygen consumption, 400. Total O2, or our oxygen content, 18.5. Mixed venous, 14.5. Multiply that by 10. So 18.5 minus 14.5, that's going to be 4. And then we'll multiply that by 10. 4 times 10 is 40. Just working left to right, bringing stuff down as we go. So, 400 divided by 40 is 10. So our cardiac output using the FICK equation is 10 milliliters per minute. And there we go, guys. We use the FICK principle. All right, guys, we are talking ejection fraction. Ejection fraction is the derived variable providing estimated or estimate of ventricular contractibility. Normal is 0.5 to 0.7. Lower than 0.3 is associated with compromised cardiovascular function and imminent heart failure, which is why this equation is so important. So let's go ahead and read our sample question here. Calculate the ejection fraction of a female patient with a stroke volume of 45 milliliters and an end diastolic volume of 130 milliliters. Okay. Pretty basic, simple math. You just know, you got to know where to plug it in. So our stroke volume is 45, and our end diastolic volume, 130. So our ejection fraction is 0.34 milliliters. And it is just that simple, guys.